If BM25 search feels slow, scoring fewer documents is the real trick. WAND MaxScore and Block-Max WAND show how top K retrieval skips work safely. After this, you'll understand how to assemble a pipeline that compares skipping plans and returns exact top documents with less scoring. I'm Professor Pi, teaching search and IR with simple Python. Large text collections make exact scoring expensive. In a search pipeline, you want the same best results, but with less CPU. WAND MaxScore and Block-Max WAND are practical ways to avoid scoring every candidate while guaranteeing exact top results. They are about proving a document cannot enter the top list, then skipping it. That saves work and reduces latency on queries that touch many documents. At a high level, these techniques use optimistic bounds. Compute a high but safe estimate of how good each term or block of documents could be. If that optimistic score still cannot beat your current top K threshold, you skip exact scoring. The optimism must be safe so that skipping never changes the true top K. Strengths are big speedups on long queries and dense corpora. The weakness is the cost of maintaining bounds and metadata. We will build a tiny teaching pipeline that starts by scoring every candidate, then adds term-level bounds, then applies WAND pruning, then max scores early stopping inside a document, and finally block-level bounds for Block-Max WAND. You will see how each change reduces exact scoring while preserving the reference ranking. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Now we start with a clear baseline that does no skipping. This snippet builds the exact baseline by fully scoring every document that matches the query. Slow lexical retrieval starts here. Every candidate gets all of its matching term contributions added, even when many candidates are obviously weak. The postings dictionary is a tiny inverted index. Query selects 3 terms, and scores accumulates document scores exactly. Sorting by score and then document ID gives a deterministic top, which later snippets must preserve. The visible output shows the reference top K result that every skipping strategy has to match. With the baseline in hand, we need a way to prove when a document cannot win. The next step computes those optimistic per-term contributions. This example computes the score ceilings that WAND, MaxScore, and Block-Max WAND depend on. A retrieval system can skip only when it has an optimistic upper bound, proving that a candidate cannot enter the current top K. Here, UB stores the largest contribution each query term could make, while lists makes document lookup easy for the small example. For doc, the real score is much smaller than the query level bound, which is normal because bounds are intentionally optimistic. The visible output shows the gap between actual score and safe upper bound, which is the room pruning algorithm's exploit. Knowing bounds, WAND shows how to skip whole documents by combining optimistic contributions across terms. The next snippet applies dynamic skipping while keeping a top K heap. This code applies WAND-style dynamic pruning while maintaining a top K heap with heapq. Once the heap has K documents, theta becomes the score to beat, so a candidate whose optimistic bound is not high enough can be skipped before exact scoring. The loop is compact for teaching. Production WAND advances posting list cursors instead of scanning docs. Heap push and heap replace keep only the best results seen so far, and scored counts how many documents were fully evaluated. The visible output shows the same top K as exhaustive scoring with fewer exact document scores. WAND skips entire documents, but many queries have many terms. Often, you can stop scoring a document partway through its term list. MaxScore orders terms to let you stop early. This snippet shifts from skipping whole documents to skipping late-term reads inside a document. MaxScore orders terms by UB, tracks the remaining possible contribution in rem, and stops when score plus rem cannot beat theta. That matters when queries have many terms. A candidate may need only a few postings reads before it is provably unable to enter the heap. The code still uses the same heap shape, so the final ranking contract stays consistent with earlier steps. The visible output shows the preserved top K and the number of term reads MaxScore needed. Block-Max WAND pushes pruning up one level to blocks of documents. If a whole block cannot beat the threshold, you skip reading every document in that block. This example adds the extra index metadata that gives Block-Max WAND its practical edge. Instead of asking whether one document can win, Block-UB asks whether any document in a small block can still beat theta. If the block-level optimistic score is too low, the code skips every document in that block without exact scoring. Smaller blocks usually create tighter bounds, but require more metadata. Larger blocks are cheaper to store, but may skip less. The visible output shows the same top K result plus skipped documents, making this a tiny exact retrieval baseline with measurable pruning. These methods share one clear idea: compute safe optimistic bounds, then use them to avoid doing full scoring when you can prove a document can't make the cut. That gives big wins when the collection is large or queries touch many documents. But remember the trade-off. Bounds and block metadata consume index space and add update complexity. A practical next step is to tune BM25 parameters K1 and B on your own corpus, while measuring how pruning rates change. Small changes in K1 and B can shift term contributions and alter how often WAND and Block-Max skip, so tune on a validation set you care about. If short practical IR helps your work, subscribe and watch the IR videos.